Submaximal intensity and hydration. This is typically for a marathon. The system uses the aerobic system. The fuels are oxygen, fats, carbohydrates and protein. Fiber is slow twitch. The waste is lactic acid or hydrogen ions, and other products are carbohydrates for the Krebs cycle and H2O water for the ETC cycle. The characteristics are it has a high VO2 max of 17 ml plus, fractional utilization, high power output at lactate threshold, muscle oxidative capacity, economical technique, fat oxidation at high power outputs, is fatigue resistant, and oxygen delivery is determinant of VO2. Glycogen depletion. Glycogen depletion. These graphs are showing, so the graph on the left is showing over time muscle glycogen depletes, and after 3 hours it depletes down to under 20%. This shows during light exercise, so maximal exercise, submaximal exercise like this exercise, that glycogen doesn't deplete, whereas during moderate and heavy exercise it depletes more. Well, it depletes a little bit during light exercise, but not as much. And the right image shows stored glycogen over days of training. Fat stores. Fats are an energy source at first, then they are converted into carbohydrates and protein, which can then be used as an energy fuel. They improve performance because it means we get more energy and we can work at the same intensity for longer. H2O. The effects of dehydration or water loss are: at 2% of water loss there's impaired performance, at 4% there's a capacity for muscular work declines, 6% heat exhaustion, 8% hallucination, and 10% circulatory collapse and heat strokes. In the top right image you can see that aerobic capacity significantly decreases from 97% to 45% from significant dehydration. This is because we lose weight, so after 1 to 2% of weight loss, body temperature increases. At 3% there's a significant increase in body temperature with aerobic exercise. At 5% weight loss there's a significant increase in body temperature, decrease in aerobic ability and muscular endurance. There's a possible 20 to 30% decrease in strength and anaerobic power, and a susceptibility to heat exhaustion. At 6% of weight loss there's muscle spasms and cramping. At 10 or more there's excessively high core body temperature, susceptibility to heat stroke, heat injury and circulatory collapse with aerobic performance. The bottom right image basically shows dehydration, and that the bottom right image shows that all of them decrease in performance, but the least with carbohydrates and water, and water's next. Carbon dioxide is transported into the blood in 3 ways. 3% of it is dissolved into the blood plasma. 23% is taken as carbaminohemoglobin, and 70% becomes carbonic acid. Carbonic acid is bicarbonate plus hydrogen ions, and hydrogen ions increase the acidity or decrease pH. Neuromuscular calcium ion. The first of the 4 stages are ATP binds to myosin, causing it to detach from actin. ATP then becomes ADP, which releases energy so that the myosin heads convert into what is called a cocked state. The third stage is where calcium binds to troponin, which exposes the actin sites that myosin can grab onto and pull for the sliding filament theory. Myosin then completes a power stroke pushing on the actin, completing the sliding filament theory, or the cross bridge cycle. During muscle contraction, the calcium ions are released into the cell, which causes the filaments inside of the muscle fiber to contract. But during relaxation of the muscle, calcium ions are pumped into storage, allowing the muscle filaments to relax. Calcium which is pumped at the sarcoplasmic reticulum can leak and will lose calcium ions. This decreases the calcium release from the sarcoplasmic reticulum, which reduces or weakens muscle contraction. Nerve impulse. Acetylcholine is required to transfer the nerve impulse across a synaptic gap at the neuromuscular junction and to initiate muscle contraction. The muscles work in an all or nothing law, and there has to be ACH or acetylcholine above the threshold and a contraction occurs. But if there's not enough acetylcholine, then the muscles won't contract because of the all or nothing law. If not enough ACH, acetylcholine gets to the receptor sites, there's not enough muscular contraction, and therefore there's fatigue, which affects for performance because you have to decrease intensity, which means you're not working as hard and performance will decrease. Cholinesterase depletion or excess. Cholinesterase is an enzyme which breaks acetylcholine down after this role of the all or nothing law and gets it ready to be used. For another muscle contraction to start, there needs to be no ACH or acetylcholine in the synaptic cleft. If there's too much acetylcholine or not enough cholinesterase, then there is no new action potential generated, which causes fatigue, which reduces performance because intensity has to be dropped. Ways to reduce or avoid fatigue. Carbo loading is one of these ways to reduce or avoid fatigue. Athletes, especially long distance like marathon runners, would do this. Carbo load a few days before an event, which increases the amount of glycogen in the liver and glucose in the muscles. It delays fatigue, and there are two methods of glycogen loading. Method 1 is to reduce glycogen levels for the first few days, to eat a low carb diet and continue to train, and then in the final few days you reduce your exercise levels and eat lots of carbohydrates. It's called supercompensation, so the body is tricked into thinking it doesn't have enough carbohydrate stores, so therefore when you eat those lots of carbohydrates in the final few days after it's been starved of it takes all of them in and stores them, thinking you'll definitely need them. The advantages are that it stores more glycogen and there's more water to store glycogen, but the disadvantages are it's a 7-day process, so fatigue is felt early in the week, and it uses proteins or muscle for energy. Method 2, 3-minute high intense activity a day before a race, opening up a carb window, then immediately eat the carbohydrates within 20 minutes, and a low proportion of the SO fibers means there is a quicker fatigue, which will reduce performance because you have to drop your intensity quicker. oxygen deficit and EPOC. There wouldn't be an oxygen deficit, or it would be very small, and same with EPOC, because you don't have any oxygen to repay, because it is an aerobic system rather than anaerobic, and so you're not borrowing oxygen because it is an aerobic system. A lactic fast recovery. This wouldn't be very big because we mostly use the slow lactic acid recovery, and the alactic fast recovery role is to resynthesize ATP and PT, replenish all myoglobin and hemoglobin with oxygen, and it is achieved in 2 to 3 minutes. But 50% of phosphocreatine stores are resynthesized within the first 30 seconds, and it uses an additional 1 to 4 liters of oxygen. This will be very small because we need to use mostly the lactic acid slow component of recovery. So this is obviously going to be larger because we need to use this because we're doing longer aerobic exercise. So it removes carbon dioxide by the plasma and carbohemoglobin. It maintains ventilation, circulation, and body temperature, which is important for marathon runners. It needs 5 to 8 liters of oxygen and can take minutes up to hours. It removes, oxidizes lactic acid, and it replenishes muscle glycogen stores, important for marathon runners and aerobic exercise. It removes lactic acid during recovery because it converts it to pyruvic acid, which then re-enters the Krebs cycle, and 65% is converted into carbon dioxide, and H2O 20% is converted into glucose, and 10% is converted into protein. Breathing remains slightly elevated after exercise to increase oxygen delivery to the tissues and carbon dioxide removal from the tissues, and heat production is higher than heat removal during exercise so that temperature can stay elevated after exercise. 80% of oxygen consumption ends up as heat, and 20% ends up as mechanical work. Most heat is dissipated. At high exercise intensity and environmental temperature and/or humidity is elevated, resulting in an increase in body core temperature, hypothermia resulting in fatigue, which causes intensity to drop, so performance worsens. If you're too hot, it affects the hypothalamus, vasodilation of surface capillaries, the shunt vessels constrict, you sweat, you decrease metabolic, and your hairs lie flat. If you're too cold, it affects the hypothalamus cold center, vasoconstriction of surface capillaries, shunt vessels dilate, decreases sweating, increases metabolic rate, hairs stand on your ends, and you shiver, resulting in your body heating up. Nybo and Setcher 2004, Todd et al. 2005 said hypothermia can affect both central and peripheral processes involved in the production of muscle force and power. Pre-cooling strategies. This is cold water immersion and ice slurry ingestion. Cold water immersion is where the body is immersed in water of an ambient temperature below the human thermoneutral zone in water 33 to 34 degrees. If the cold stimulus is of sufficiently low temperature and provide for long enough, heat loss will exceed heat production, causing a reduction in core temperature and increase in heat storage capacity. Ice slurry ingestion is phase change of solid ice to liquid water, requiring a large transfer of heat energy into the system, known as the enthalpy of melting. When ice slurry is ingested, heat energy is transferred into the slurry mix from surrounding tissues rather than being stored in the body, reducing core temperature and increasing heat storage capacity.